In a TED Talk, you compared the difficulty of finding exoplanets similar to that of looking for a firefly next to a searchlight that's quite far away. Let's linger on some of the problems. What are these obstacles that are in your way if you're trying to look for exoplanets? What are the challenges that exist that you're trying to solve for?
Right. Well, the main challenge is that any exoplanet is right next to a big, bright, massive star. So like on its own, we could easily find and study planets with our telescopes. But the fact is that the star is so big and massive and bright, it gets in the way. So the challenge is that our techniques have to be able to work within that star being right there. And like what that translates to is that our detection and our characterization techniques, let's just say they have to go to many decimal places. So like if you were going to build a table like this, and let's say this table is 4 feet by 2 feet, and you're going to build it. You're going to go to the store and you're going to buy some wood, but are you going to buy 4.000000 feet or just 4 feet?
Right.
So our techniques, it's laughable. We have to go to like 4 decimal places to 5 decimal places, sometimes to 10 decimal places, depending on the technique. We can't do the 10 decimal place yet. And so our biggest challenge is whatever measurement we need to make, it has to be so incredibly precise. It's pushing the limits of like our detector technology, our computer software, et cetera. So I can give you a more specific example if you'd like, but that's the bottom line.
Let's go for the specific example.
Sure. Well, the specific example is, let me think for a moment. I mean, there's so many examples, but our most common way to find planets right now is the so-called transit technique. So if we imagine that we have a star, well, let's see, let's take, it's a rectangular star, and a planet is smaller. The planet orbits the star, like it could be orbiting in the plane of the sky like this, but some of them, they're orbiting in the plane of your viewpoint, and you can see it go in front of the star as seen from your viewpoint. Mm-hmm. We call these transiting planets, because it transits the star every orbit. Well, what happens is we can't spatially resolve the star. We just see the stars like a pinprick of light, but we can watch that light dim by a tiny amount, actually. And so we have a telescope, a space telescope called TESS, Transiting Exoplanet Survey Satellite. It monitors tens of thousands up to like millions of stars at one time. And our computers look for this tiny drop in brightness that indicates a transiting planet. And these transits, they range anywhere, dimming of the star ranges anywhere from 1 part in 100 to 1 part in 10,000 or even smaller. Yeah.
So you mentioned one of the big challenges of detecting exoplanets is because they're next to such a bright star, and the transit technique is one way of detecting exoplanets. You've actually listed down many of the techniques, technology solutions that we can use in your book, Exoplanets, this book that you put together. You've also spoken about direct imaging, coronagraphs, the Starshade project, radial velocity, microlensing. I'm going to ask you an unfair question. This is going to be the first of many, I'm sure.
Okay. No.
But can you summarize many of these different techniques? We already spoke about the transit technique. Mm-hmm. What are these other techniques and technologies we can use to detect exoplanets?
Yes. Well, we can divide them up into 2 categories, direct and indirect.
Okay.
So transit is indirect because we're not seeing the planet. We're effectively seeing like the shadow of the planet. And it's not even really, we're effectively seeing like the shadow the planet is casting on the star. It's not even really that. There's indirect and direct. Indirect is like transit, where we're looking for an effect of the planet on the star. Right. We have one called the wobble method or radial velocity. You know, the planet orbits the star, and the star is also moving due to gravity of the planet. We say the planet and star orbit the common center of mass. So the star is also moving, and we can measure that star wobble, actually. In fact, we're measuring the line of sight motion of the star down to levels of like centimeters per second. We can measure the star's motion along the line of sight to walking speeds. And that's how we can infer the presence of the planet. Indirect. We have gravitational microlensing, indirect. And then we have direct techniques. And those involve blocking out starlight so we can see the planet directly. And that means direct imaging. See, because we're seeing photons directly from the planet. We're getting rid of the star. Now, not everyone will have done this, but being in New York, I know you got a lot of snow this year. Have you ever tried to take a picture of a person in the snow?
Yeah, I guess.
It's really hard because either the person's all dark and the snow's really bright.
Right.
Well, usually that's what happens because our detectors can't handle the dynamic range of the bright snow and like the just dark regular person.
Right.
We have that same problem when we try to look at a star and planet together, the star's so bright, just like the snow, it overwhelms the image. So we literally have to find a way to block out the starlight using various techniques to see the planet directly. And we've done that for very hot, young, massive planets that are really far from the star, that are shining with some of their own energy left over from when they formed.